emisión del panel de control de GoToWebinar para que los asistentes le oigan. El sistema le avisará cuando comience la emisión. La emisión está comenzando. Todos los asistentes están en modo de solo escucha.
Genere è meglio Academy, però.
Perché questo già non
È già
una
quello,
statistica. E poi ti metto anche dei pointer, ti metto questo qua,
sì.
dove?
Qua.
Ok, questo è consegnato. Ah, ok. Per il momento mi serve a me
sì,
e poi
bene.
ci mettiamo, mo ti scollego, perché questo che dobbiamo.
Ci voleva il sistema quello della normanza. Che bello.
Hi, Gabby, can you hear me?
And we have 5 minutes. Io ho lasciato così, non so perché poi si è spento. Senti, penso che la secondo che audio funziona o di nuovo aspetti. Di nuovo delle collegate prima c'erano sharing out, ok. Naharika Brava, Shandila, okay. I don't know whether they can hear me or not.
Gabriela.
Can you hear me? Can you confirm that you hear me?
Gabriela, can you hear me? Hi, Gabby, can you hear me? Yes, we can hear you.
Okay, so thank you. We are still waiting, maybe other 5 minutes, and then we will start our second seminar. Okay, just be there. Mauro, che foto?
È vecchio, lo so, io devo aggiornare
No,
qualche...
non devi, sì, io la so online. So I put also this one.
Che qua la stanza, qui c'è lo specchio di luce.
Sì.
Prisma.
Emozionata?
No, è il webinar.
Ci sono...
No,
questa volta ci sentono, sì.
Non ho mai fatto un webinar.
Ecco, ci stanno per il momento tra i 15 siamo.
Chiudi nella sala.
E vabbè, sempre siamo. No, no, allora uno in meno, perché uno dei staff sono io.
Devi fare qua. Sì. Però ce l'hai il microfono? Sei la sala.
Sì. Mentre loro stanno, come si sente con il microfono?
Quale vuoi questo qua?
No, quell'altro, il malato, ecco. Puoi alzarti e parlare, perché tanto metti quello lì e tutti vedono, se tu questo qua metti così e ti vedono.
Cioè metto così.
Prova un po'.
Prova.
Cioè, dove tu vuoi mettere qualcosa? Meno. E poi
Metto così.
in questo momento sei ripreso in quella telecamera. Quando poi parlerai tu, comunque tu prenderai
quella
te
mia?
stesso e la
Sì.
tua telecamera. Sì.
Con questa,
Cioè, però sempre con
allora,
una finestra piccola perché loro vedono comunque il
sì.
monitor che dà la presentazione.
Vabbè. Ma devo attivarlo?
No, è attivo da solo, io ti vedo da qua, vedi.
Non devo fare...
Cioè, scusami, ma tu sei collegato, non ti sei collegato su GoToMeeting, no? Allora ti vedono dalla mia telecamera, va bene?
Io posso collegare. GoToMeeting o GoToWebinar? No, devo farlo col link. Il link del...
Vedere questa
Col link
telecamera.
devo...
Ti hanno mandato un link.
Sì. Io c'ho anche...
Se tu... Allora ti posso vedere un po'. C'è CVR 16. No. Mauro no. Ok.
Ecco. Sì, ora sono collegato.
Allora ti posso fare presente. Io non ti vedo.
Intanto metto elimino l'audio.
E mi sei, ok, ho visto che questa lì nel stanza. Allora, se faccio il tuo video oppure audio, ok. Non lo so. Okay.
Dicevo allora.
Poi anche ti vedono anche se tu metti qua e tu parli così, vedi che ti vedono se tu alzi. Come? Non ti piace questo? Non deve
Va bene.
Oh, good morning to everybody. Very welcome to the seminar series of extracellular vesicles 2020 at Napoli. It's entitled, the series of seminar is entitled From Membrane Biophysics to Drug Delivery. And now we arrive to the second seminar today. I just wanted to highlight to those who were not joined the first one, what are our main aims and who are sponsoring these seminars. So we mainly would like to bring together researchers who are active or would like to enter to the field of extracellular vesicle research. And we mainly want to promote the collaboration in our region, here in the Campania region, because the society, the extracellular vesicle society in Italy is just formed, and we would like that in this region get his role in this society and in extracellular vesicle research. So we basically promote research in all types of vesicles, small, large, plant-derived vesicles, cellular-derived vesicles, so any type of vesicles we are interested. From basic science to applied science, and we would like to really to discuss, giving platform to discuss all your thoughts and research innovations or whatever problem we have in this field, using this occasion to meet here regularly. So as we said, it's 10 seminars together. And actually, it's all sponsored by the Italian Society of Extracellular Vesicles and also by the VES4US consortium. VES4US is a European PET Open project. And actually, our speaker today, I will introduce soon. He's also from the VES4US, he's the VES4US partner. So today's lecture is basically sponsored by VES4US. I wanted to highlight that we have something like 20 attendees using GoToWebinar platform today. We hope that it will increase from week to week. So you can use the connection, which is this one, anytime when you want to connect and see everything what's happening here online. So we meet every Wednesday at 12 p.m. So I hope to see you also next week. This is our program, the 10 seminars. I don't want to describe all of them, but the first was by Veronica, and Veronica is still with us, so it's a special thanks still to her because of that wonderful seminar of last week. And today we have Mauro Manno, and he will talk about biophysical experimental tools for EV structural characterization. So this is our very quick agenda of today. So after this welcome and introduction, Mauro will give a lecture which is about 30 minutes or something more, and then we can discuss in more details, hopefully that one. And then we would like to go for pizza today. So everyone who is here and can join us, we are happy to. Last week, okay, yes, it was last week and it's still today. But the pizza, I mean, last week Mauro was not here, but Veronica was here. So it's just the title. So I would like to then really welcome Mauro Manno. He is a researcher at the Institute of Biophysics of the National Research Council of Italy in Palermo. He did his master's in 1996, if I can say that, in physics from the University of Palermo. And then he was in 98 a visiting scientist in MIT at Cambridge. And in 2000, he obtained his PhD in physics. It's still at the University of Palermo. And in 2001, he obtained a permanent staff position. In 2010, he was a visiting scientist again in Cambridge, but at CIMR. And this time in UK, sorry, yes, that's right. And then in 2017, He won a very nice fellowship, which is a Smart or Valley Fellowship, if I'm not wrong, which has been financed by Horizon 2020 MSCA Action. So, seeing research interest of Mauro, I think we will learn something more today, but his research activities mainly focused on the fields of molecular biophysics and chemical physics, using several experimental techniques and setups. So mainly static and dynamic like scattering, UV and infrared absorption, emission spectroscopy, X-ray scattering, differential scanning calorimetry, circular dichroism, and chromatography. And he's also very interested in developing new theoretical and statistical tools, computational and biological techniques. He also uses it in collaboration with different colleagues. And in the last few years, Mauro's interest turned towards vesicles. And I think today we will learn something more about this one. So please enjoy the talk of Mauro.
Thank you. Really nice introduction. It's a pleasure to be here. So thanks to the Institute of Bioscience and Bioresources, the IBBR, and also to the Vita Society of this event, and especially to Gabriella for the invitation, and also for setting this seminar series on EVs. So it's very important initiative also. And may I start?
For you.
Sorry. Gabriella, may I?
Yes.
Yeah. Okay. So today the idea is to bring you to another topic related to EVs, so to bring you to the biophysical side of EVs. And of course, before doing this, since this is a seminar series, and maybe someone was not here, just some summary of previous episodes. But very quick. So extracellular vesicles. So in this case, a summary of the seminar of Veronica Flick. So what are extracellular vesicles? A nanoparticle surrounded by a lipid bilayer, and they have a cargo with different molecules, RNA, or proteins, or other things. And the biogenesis was the topic of the previous section, the previous seminar. Okay, this is in this picture, of course, we have our view from the Monreale Dome, from the Monreale Cathedral of the birth of vesicles, but actually they originate from cells, so from the multivesicular bodies, where they are called typically exosomes, or from the budding of the cell membrane. And their fate is, of course, to be uptaken by other cells by different mechanisms, so endocytosis, or diffusion with the cellular membrane, or some more specific receptor interaction. And of course, they are so fascinating because of their function, because they are actually the way our cells communicate among each other. And of course, some years ago they were thought to be just the shuttle for garbage, but now it's very well known that they have an important functional role. And of course, they have a lot of pathological implication. Mainly, one is they can activate immune response, or they have a role also in cancer to enhance or prevent the growth of cancer cells. And there are many studies in this field. And of course, there are a lot of interesting and potential applications related to extracellular vesicles. They are they are used also to make liquid biopsy, because you can take the vesicles from body fluids and use them as marker for many pathologies. So you can use for therapy, mainly as drug delivery systems. They have a lot of very well. So can I go back? Should I? Sorry. Yeah, I was saying they have a lot of interesting properties. The main one is yeah, the one of the most important is that they are biocompatible, so they can they have no toxicity essentially, and they can also cross for example, the blood-brain barrier. So this is very important for drug delivery system, and also it's very important they can provide cross-kingdom communication. So you can, for example, derive vesicles from natural sources and use for humans, for example. And actually our project, the VES4US project, is sorry. The VES4US project is that Gabriela was mentioning, and is sorry,
no, it was not. They were not hearing you before. No.
Okay. The VES4US project is about the sorry, Gabriel is not working.
But not coming to her.
No. Some technical problems. I was anyhow. I go ahead. Then hopefully you can see my slides. Yeah, the VES4US project is a European project with a beautiful consortium of people working with different fields, complementary expertise, and it's about the production, the isolation of vesicles from natural sources. And of course, the functionalization and the tested activity and the characterization of these vesicles. Yeah, this was the previous slide. Yeah, okay. Maybe now it works. Yes. Okay, it works. Yeah, okay. Yeah, I was saying production, isolation, all the many uses of this project, characterization, which includes the quality control of extracellular vesicles, and they use for different fields, for biomedicine, nutraceuticals, cosmetics, and others. And so, what about the sources? Of course, natural sources. Here in the lab of Gabriela Fox-Falvi, there is also a long expertise on these natural sources, which may include lemon, tomato, or another green sources that is more specific to our project, which I'm not disclosing today because there is a patent processing that it will be soon disclosed. But today, of course, I'm not focusing on the source, but on the tools related to the structural characterization of extracellular vesicles. So, of course, there are a lot of requirements for this characterization. The International Society of Babies has put in these many indications for the minimal information studies for the identification and characterization. And this table I'm not going through was our revised view for our systems. And today I will just focus on the few of these characteristics that are related to the vesicle identity and to the structure of vesicles. And to do this, I try to give some biophysical perspective. And of course, one of the main biophysical tools is the way of thinking this object in a different way. I mean, Albert Einstein was, there is a sentence attributed to Albert Einstein. It is the science is 1% imagination and 99% transpiration. And maybe today I want you to focus on the imagination. That is maybe one of the tools important in physical, in the physical science. So maybe what you see. So let's start to imagine something. What you see in this picture. I don't know. Maybe you see an atom. Maybe I can see a boa eating vesicles. So actually, this is a 3D reconstruction of an extracellular vesicle imaged by atomic force microscopy. And yeah, the reason why I was thinking to the boy eating the elephant of the Petit Prince is that because of this curve here. So these curves are the profile of taken by IFM microscopy. Our IFM works in this way. There is a tip. It actually is scanned to the surface where the sample is deposited, and this tip probe the surface of the object deposited on this surface. And in this case, with this vesicle, we are using an R-tip. So to use an R-tip means that there is a lot of interaction of the tip with the membrane, and so we observe a deformation of the membrane in the central part of the vesicle. And what happens if we use another tip, a soft tip, let's say with a lower elastic constant? So when we repeated the experiment with a soft tip, what happened is that this surface becomes flat again. So essentially the interaction of the tip with the membrane is less consistent. So the membrane is not able to deformate. The tip is not able to deformate the membrane. And you can imagine this open a lot of to study the mechanical of these vesicles, and because you can, for example, imagine to say something about the bending of the membrane due to when you probe when you apply one force, another force. So there is and this bending may be due to different things. So maybe due to the composition of the membrane or to the V content. There are some study in our lab on this to study more this aspect. And of course, the atomic force microscopy can be used with this mode, which is called atomic force spectroscopy sometimes. But it can also be used to take images of the vesicle, so to look at the morphology of the vesicle, and you see this kind of our vesicle from our natural sources that appear in this picture. And of course, other technique can be used to do this image, other microscopy technique. Just a few examples from the same vesicles from a picture that was taken by Cryo-10 by our collaborator in Mainz, but Katerina Lancaster, or other from TEM that we have from the lab of Veronica Idlich in Ljubljana. And of course, there are many microscopic techniques that are very useful to probe the morphology of the vesicles. But as also the Society of International Vesicle recommends, we have to also to expand the field, to probe the heterogeneity of different vesicles, and so to image as much as possible differently. So this is what we've done with the AFM, and we have seen a lot of vesicle different type, and in this picture also some vesicle aggregates. And what we can also do with AFM is to go further and see and try to measure the size distribution of these vesicles. To do that, we have to use some trick. We have to attach robustly the vesicle of the substrate. So the substrate is functionalized. Then we image as much as possible to have enough statistics. Then with a non-made software, we can identify the single objects, measure the size, and derive the distribution of this object, which in this case is an average size of about 60 nanometer. And this is a very well, atomic force microscopy has a very high resolution. It's a single particle technique, but in any case, it's related to the kind of sampling that you are making, the way you deposit the substrate. Probably, if you want to know something about the size distribution of this particle, you have to go to some other techniques that are related to the whole ensemble of particles included in your sample. And to do that, there are many options. Maybe the one I think is the best is for light scattering. Light scattering is a technique that uses a light on the light of a laser on one sample, and then this light is detected at the light is scattered by the sample and detected at different angles. And what is very nice about light scattering is that you know exactly what you are measuring. So the signal of scattering is proportional to the square of the mass, to the number of particles you have, and to a function which is related to the shape of the particles. You can also make the correlation of the scattering field, and you observe you have this quantity that I got in bracket, which is the mean square displacement, which is what is used to measure the diffusion coefficient of this particle, and then the size of this particle. And this is depending on the size of the particle, you have the fluctuation in the scattering intensity, which are more fast, as in this blue signal, or slower if the particles are larger. Then you can correlate the signal and obtain this typical measure, which is called autocorrelation function. So this is a scattering technique which is called DLS, or photon correlation spectroscopy. And you can have a very nice, well, I'm wrong here, a very nice introduction to this, to a recent paper by the boss here in the lab of Veronica just appeared last year, actually, in cells. Very nice introduction to the use of this technique to extracellular vesicles. And there is an advice that says you are muted. I don't know. Can I continue? Okay, I continue. Yeah. Okay, you can use you can analyze these signals. I don't go very much into the details by extrapolating to low time, and you can use what is called the cumulant technique to measure the average size of this molecule. However, these samples are these particles. These samples are typically heterogeneous, so you have to figure out how to treat this heterogeneity. In this case, we have a scattered signal, which is the sum or integral of the many contributions of particles from different sides. In this case, what you do, if you know what this type of integral is, you can do what is called a Laplace inversion. It's that you essentially you derive distribution from the by making, well, I want to go in detail. You make this, you apply a defined algorithm, and one famous one is called Contine. It's the one that is used in a commercial instrument. And you obtain, for example, for this sample, talking about this kind of distribution, which is typically very broad, not much informative, and actually in commercial instrument you probably see this kind of picture on a logarithmic scale, just to have to pretend that you are actually measuring something which is sharper, while typically is a quite broad distribution. You can do better with a better analysis, and we try to say that we can do an analytic fit to this kind of function, which gives you a more informative result, and you probably can detect in this kind of analysis the size of the vesicles, and sometimes, as you see in this little peak below 50, sometimes the presence in the samples of 3 proteins, for example. But of course, I don't want to go into details of this how this distribution is derived. So I better pass to describe other characteristics of this technique. And one interesting, useful thing to observe is that sometimes puzzle people is that the distribution that you are measuring with light scattering is weighted with the mass of the object, so with the size. So essentially, because you have the weight in this interval, this sum is related to the number distribution, which is the number of objects you have of a particular size, but it's weighted with a form factor and with the square of the mass. So there's nothing wrong with this kind of measurement. Only if you like to have an intuition of where is the measured number of particle, which is the size of measured number of particle, you can use some tricks, some approximation. So if you make the hypothesis that all the mass, the major part of the mass of the particle is on the surface or close to the bilayer, you can model the vesicle as an hollow sphere, and then of course make some approximation related to the dispersity and transform the weighted distribution to a number distribution. And this gives you, of course, a mode of the distribution which is obviously lower than what you measure with the weight average distribution. And what is interesting, for example, in this case, is that this number distribution is equivalent to the distribution that was found by using AFM. So this essentially is very encouraging, because it means that the sampling that we were doing with the AFM is not so bad, and that hypothesis, the rough hypothesis we are making to derive the number distribution is not so bad either. So it's very encouraging. So just to mention other technique that can be used to address the size distribution. Another powerful technique is fluorescence correlation spectroscopy, which is very to the photon correlation spectroscopy. It essentially measures the time that the particle required to enter and exit a confocal volume. So of course, the vesicles need to be tagged with the fluorescent probe, and then you can measure and this is what we've done in Palermo with this probe, and you can measure the size distribution. That is, of course, the shape of this distribution depends on how you are efficiently labeling your sample. Again, let me mention another way to use scattering, another popular way to use scattering to measure the size distribution. It is to essentially to use a microscope to follow the particle, to track the particle, and measure the quantity in bracket, the mean square displacement of the particle. So you see how it's diffusing the liquid with a microscope, and then by doing this, you can measure the diffusion coefficient of the particle itself. This has now becoming a popular technique. It's called nanoparticle tracking analysis, and if you use with this vesicle, you can obtain a distribution which is slightly higher than what you observe with DLS. You can also use this fluorescent probe and analogous information. But you can notice that sometimes with the NTA, you are sampling your particle, you obtain a better sampling of larger particles than smaller particles, so you have a bias related to the sampling. So essentially, what I was in this list of this technique, I try to tell you that you can use different methods essentially to address the heterogeneity of this particle, which is the main problem. And probably the most robust measurement that you can make is to determine the other sides. And this can be directly done by DLS, for example. And then you can use you can measure the size distribution by using some analytical sheet and derive the size distribution. But of course, if you want to, if you really prefer to know where is the major number of vesicles, so where is the in which kind of distribution you should use to have the major number of vesicles, maybe I can propose you a rule of thumb, that is to use an average that is between the moda of the number and the intensity distribution, because of course the intensity distribution weight consider more the larger size particle, while the number distribution introduce an approximation maybe too rough. So you can be confident that in this range there is a major number of particles. So well, this table I'm going to was just to list all the techniques, the single particle technique that can be used, that are the microscopies or other ensemble technique, and also there are some non-scattering technique that you mentioned, like the resistive pulse sensing, which is also important. But not I don't want to really go through these pro and cons of these techniques. I just want to mention other important techniques to determine the characteristic of vesicles that are not related to the size, like optical spectroscopy, that is luminescence, to determine the protein content, or sometimes some probes that are used to determine the property of the membrane, and also other work that is ongoing in our lab to use infrared spectroscopy that is very powerful to determine the content of protein lipid, because from an infrared spectrum you can really assess different parts related to the lipid, to the protein, or to the sugar that are contained in this vesicle, that are heterogeneous systems. So, and of course, atomic force spectroscopy, I already mentioned, that can be used to determine the interaction of the tip with the membrane. But just I want to mention a little bit more in detail about one type of experiment that can be done to address the structure of the bilayer molecule. And for this, we have I'll talk about the work that we have done on Giovanni on the extracellular vesicles from skeletal muscle cells, okay, with the effect of pad methylation. But now I don't want to focus to the biological implication of this work, but just on some tools we developed to address the structured bilayer. And this is some experiment on small angle X-ray scattering. To do this experiment, you need European facilities, in Paris, for example, and you obtain this kind of pattern. These four curves were related. The lower curve was small vesicles of obtained from skeletal muscle cell, while in the higher part you have the large vesicle or vesicle treated with inhibitor palmitulation. But again, now I want you to focus on this feature, on this hump that is in this curve. It is related to a dimension of 5 nanometers. So it's related to the typical dimension of the bilayer of this of the bilayer of a cell membrane or a vesicle membrane, and this is because the electron density of the lipid bilayer is different if you look at the polar head or the hydrophobic tails. So essentially, X-rays see a contrast in the electron density related to the bilayer structure and can detect the structure of the bilayer, of course, an average information. And in this case, we were able exactly to look at this dimension. But there was one criticism that was taken, that maybe also the same characteristic length is typical of protein, of free protein that may be in our sample. It typically happens in samples with vesicles. We have around free protein, free small protein. So to discard this fact, we used another technique. Is small angle neutral scattering. It's very similar to SAX, to small angle X-ray scattering, but there is one difference that yeah, to do this we went to Grenoble, picture of the synchrotron director in Grenoble, and we repeated the experiment, and again we see the SAX data show this the same hump characteristic of the bilayer structure, while this feature is not present in the neutron experiment because below, and the reason is that there is the way that X-ray neutron see the matter. They see the matter in a different way. The X-ray look at the electron density, while the neutron are more sensible to the nucleus, so to the hydrogen, to the atoms itself. So in the case of an extracellular vesicle put in a deuterated buffer, the result is that we see essentially a uniform big object with no contrast inside. So everything which is related to the double bilayer is washed out, and but we can affirm that we are not seeing a protein, free protein in our sample. Actually, these you can in principle with synthetic system you can go in further details, make a more accurate analysis and good numbers. But in this case, we were having a very heterogeneous system, so we were happy to give the main biological information, that was that in this case the large the unstructured release of vesicles, which is due to the large formation of large vesicle or to the inhibition of palmitulation, was just in a way increasing the heterogeneity of the structural organization of the membrane. It was a very experiment combining these two techniques to address this problem. So it's really an open field, and we are trying to work more in this direction. And yeah, let me just sum up. Try to do some brief idea of some tools related to this powerful system, the extracellular vesicles, and with a few examples from our project, which is these natural source-derived vesicles, and these tools for EV characterization are related to the use of microscopy and scattering techniques, essentially to address one of the main feature, but also the main obstacle to a deep study of this particle, which is the deep heterogeneity that appears in these samples, and then also there are some other possibility to use different technique like atomic force spectroscopy or different scattering technique to study the structure of the membrane by layer to use the rigidity. And then just let me thank our wonderful consortium of VES4US, and maybe time anymore to mention everybody there, but just let me mention the colleague of my institute in the Institute of Biophysical in Palermo, Samuele Raccosta, Stella Rao, Angela Paterna, Rosina Noto, Rita Carrotta, Enzo Martorana, Fabio Librizzi, collaborating with me with this wonderful project, and then the other, the other people of the consortium, and of course Gabriella Boxfalvi for this invitation again, for this seminar series, and then I thank you for your attention.
So thank you, Mauro, for this nice, interesting presentation on the biophysics and the biophysical measurements of EVs. And so it's open for yeah, what? So it's open for question, the talk. Sorry, just to give it to her.
About the synchronous laser technique, which kind of heterogeneity do you find? Can you understand difference in the possibility of the composition, or the differences are in the thickness of the quality?
The success experiment is done essentially with sample resolution. So the resolution of your structure information is quite low. So you have information related to the main length of your sample. So you cannot distinguish the composition of the membrane. What you can say is that you have a different density around related to the outer layer membrane inside. And the heterogeneity essentially in this case complicated because when you have a heterogeneous sample with different scales, all the main features that appear, like the hump I was showing before, are essentially averaged out by the fact that you have slightly differences in the sample. So it's just a complication. In this case, we have used this complication to obtain information, but essentially means that we were just able to say, okay, in that particular biological application, we observe the increase of the rigidity. The technique doesn't allow you to say what is. Sorry?
Sorry, no, it doesn't give you full information. It's just about how many different times.
If it's heterogeneous, yes, but if you can observe an homogeneous sample, you can really go deeply into the structure. In the real case, we have one single population, which was not completely the case, where vesicles coming from the right type skeletal muscle cell. You can say this is the formation.
So I'd like to ask if you think that the rigidity of the plasma membrane in the extracellular vesicles can be affected mainly from the source, the origin, or it can be due from other features like post-translational modification of the proteins or something more specific and independent from the source?
It's a great question. I wish I could answer it. But, yeah, I don't think that there are enough studies to answer this question. But yeah, the point is that the question is so interesting that we are actually, as I try to tell you, we are trying to set a series of experiments exactly to address this problem. So to probe the membrane rigidity compared to the origin, compared to the, for example, probably the most important post-rotational modification in this case is the calculation that probably we can address with atomic force spectroscopy. We can address this problem. We can probe the membrane rigidity and then try to see if some glycan chain, for example, are specifically there in the surface of the vesicle, but it's really an ongoing work. Also, a lot of work. So I think is an unexplored field. Small.
You showed very nice approaches to characterize vesicles in time. Even so, there is a chance about the transition to vesicles from different sources like mammals and plants.
Yeah, actually, well, on my limited experience on vesicles since a few years, yeah, I had the chance to work both with mammalian cells, cancerous cells, and also natural sources, and it's well, I didn't really went into the details of the composition, which is probably the most, maybe Antonella can answer better than me about this, the question of the composition. What is related to the structure, to the side, well, essentially I can tell you, but it's just an end-waving consideration, that for example, for mammalian cells, typically you observe more what I call exosomes, so they are the smaller size, while from natural sources you have sometimes a broader variety, so something like by natural means, for example, the sources that Gabriella is working with, or others that will be happy to to tell you in a few months. Well, yeah, there is a difference. I cannot say there is a systematic difference. What you have from this point of view, there is, as I said, a typical preference for the exosome for the mammalian cells. But of course, this depends on the kind of preparation that is done. Probably also have the vesicle there, and for also for the very limited experience they have with IFM imaging, I can tell you that there is a large heterogeneity also there related to the sources. So yeah, so there is I cannot give you a systematic at this point every interesting characteristic is to be explored.
So about light scattering, when you have this data, there is a model which you interpret. And then once you look on the field of other systems like nanoparticles, inorganic ones, are quite different from what we have with the research. So do you think that it could be sensible to make a better model for vesicles? Because it's rather disappointing. You have to going in advance with the assumption that you have, for example, two populations inside, and then you get repeats. If you assume that you have three populations, you get repeats. And this, I think, is a weak point of the light scattering method. So it's not hopeless, just nobody really going into this direction.
Thanks. It's a good point. You're working on this. I think you are not talking about the approximation that allow you to transform into numbers, because that is obviously not. You're talking about the actual way to fit the data of light scattering. Of course, well, in this case, okay, there is a, as you pointed, a main probably uncertainty, which is due to the number of peaks you decide on sample. It is also in common Laplace inversion, continuous measurement in a way you can work. In this case, of course, yeah, it depends on how. Well, I think maybe one a correct way is to start with a fitting with a less number of parameters, and then maybe if you need more, you can more or less safely introduce them. And of course, to fit it in a conservative way is a good idea. Then in this case, the fact about the analytical shape, and maybe we can talk about this later. Right now, of course, it would be very nice to have some theoretical derivation of a physically relevant shape for the distribution. And yeah, maybe we can talk about this later. But in this case, I was just using an expression. Again, it's not. There was no time now to go into this detail. I'm using an expression that is more like the minimum number of parameters. There is also a reason for that, which is due to the noise of the operation function. But yeah, I don't know if it's I can answer to you. I can say, but maybe continue later because maybe cannot follow me. If you think at the size distribution that is determined by the number of cumulants you can determine, it was essentially also proved by Fuse a few years ago that after the third cumulant, essentially the noise doesn't allow you to determine, it's not determined anymore. So you can maybe go just beyond the Gaussian approximation. I'm sorry for all this technical detail. That's for Veronica.
So I would like to read two questions from the audience who are connected. The first is that can mammalian cells be considered natural sources well? Or there is a distinction between natural sources or mammalian cell-derived exosomes? So this is
oh, sorry, I was using the the word natural sources, yes, just to distinguish between human, mammalian, and other sources that can be maybe used for some scale-up production or for many other exploitations. But there was not a particular distinction in that. So I apologize. I was maybe misleading on this.
Okay, but it means that they are following you, no?
Okay.
Okay, so the another question is it possible to change the EVs by the bilayer structure of the EVs in order to alter their function? So it's also a very interesting question if you can answer that.
Yeah, it's actually one of the tasks of our VES4US project, exactly to functionalize the surface, for example, to change the qubit bilayer, to change the structure, to add some features, and to use them for many purposes, so to specific tissues are specifically for many other uses. So yeah, it's really a wide open field where there is a lot that can be done in this direction.
So some more questions? No? I think I would like to say many thanks to, first of all, to Mauro, and also for you who attended here, and all of the people who are attending online. So with this one, we are closing the online section. So see you next time, which in 1 week time, we are going to have a presentation. Again, I think it's from Chiara. So it's something on the very much on the application aspect of the EV field. So matters or not in cancer cell-derived EVs. Thank you.